Okay, let's get started. Today's topic is about representation. What we are going to learn is the way that um, neural network learn representations that can be generalized in different applications. All right. So the topics that we will look at are the embedding representation in text applications, and an autoencoder, which has the network that can compress the data down to a certain level and then reproduce it back. Okay, we will take a look at what these architectures implies, and if we look at the research, you may see that the research in this area try to focus on how to reduce the dimension of data and then make use of them later on. Right, let's start. First, let's look at embedding. Right, in word in text classification task, it is important to get the representation of the word right. How do we represent the word? You can represent the word by representing it as a word by itself. It has certain meanings, right? The word meanings reflect the idea of the word, right? It has the indication of what the word is used for, and it also expressed how it is used in writing. But the thing like dictionary like this is okay for human to understand the meaning underlying the word, but it's not usually okay. It's not okay for machine learning, for the deep learning, to make use of this type of information, because this type of information summarize or explain things, the meaning of the word in terms of the context that only human know. Machine doesn't know. So there has to be somewhere else, some other method that can be utilized to use in text analysis. Such a method like WordNet, right? So instead of having the representation of word, which if you use with machine learning, just with deep learning, just like last time, we represent word as one hot encoding, right? Or as the TF-IDF score. But you can see that those representations do not reflect well in terms of the meaning, in terms of the context. One word can have different form of writing. It can have different synonyms. It can have different antonyms. It can have different words that are parts of the hierarchy. So in order to use the WordNet to represent the word, scientists in natural language processing utilize the dictionary style that kind of draw the relationship between words as graph, and then use the graph to map the words from one form to another form. In Python, usually there is a library called an LTK that you can use for lookup for the synonymous set, which will give you words that are similar to that word. So it means, do we solve the problems of context of representation? For human, maybe it might help us, but for an algorithm, for the computing algorithm, more work needs to be done, right? Because with just explanation like this, it is still unclear on how this would be implemented in the algorithm, so that it can learn the pattern out instead of having just this. So these are the problems. WordNet is a good resource, but it missing something that is in the detail, right? Proficient is listed as a synonymous as good, right? But this is true in only some contexts. In some contexts, good may mean products, right? In some contexts, good may mean the right or wrong way. So there are certain dependency that are not covered in these types of relationship. And it also missed some new word in the old compiled data like that. It is quite subjective. It depends on those who compile those lists to put the word in. And it requires human labor to create and adapt those lists, right? And you can compute the similarity of the word. You can tell whether one word is similar to another or not. Okay, so in that, and that also carry on to the machine learning application that we have seen now today. Okay, so in traditional text analytics, traditional natural language processing, if we were to represent a word like hotels, conference, motel, they might be represented differently, right? By using one hot vector. For example, the motel can be this code, while the hotel can be another code. And the dimension of such vector will be huge, it will be large, like 500,000, right? If we were to do the one hot encoding. So usually what we do would be to limit the number of words that we will cover, just like last time. In the last time, when we create a model, we limited it into certain dimension before using it in a classification model. Okay, so the problem here would arise that if you user search for the word like Seattle motel, and what we like is to have this word also match with hotel, because both are accommodation. They have the same semantic, right? In the current representation, you cannot do that, because hotel and motel are drastically different. They are orthogonal to one another, right? They are different to one another. So what is the solution? Like one solution is might be to use the word net to map from one word to another word. That might be it, but there will be problems, like because of the incompleteness, right? Some word will be missing, right? And so instead of doing that, it would be better if we could encode the word differently rather than using one hot encoding. We have different type of code to encode the word, which also carry certain meanings with them. Okay, so we can represent the word based on the context. There is a concept called distributional semantics, that word meanings can be given if they were to appear on the same location. Like, suppose we were to replace banking. The word that is similar to banking has to be surrounded by the similar context. The similar contexts are the words that are surrounding, right, the target word that we are talking about. Right? So that means for banking, this would associate with crisis, with unified regulation, with systems, like some word like this that are in the same context as that. Right? So keep in mind that when we are talking about context, we are talking about the word that would appear in the same situation. We want our representation, the encoding of the vector, to reflect this out. How would we do it? Let's see. Okay, let's look at this first. How do we create a representation that is more contextual than one hot encoding? One simple approach is to use a different, instead of using just one, we can do it by encoding the word based on the word cross document. Represent it by using the matrix of word document matrix, like this. For against, it appears in document 4, 7, 8, and 9. So the code will be based on the appearance in the document. For H as well, think about this as something like term frequency, right? When you create a term frequency or TF-IDF, is actually the encoding of the word. But well, in that sense, we represent everything as just happened, right? But here, instead of representing it as one hot encoding, we will represent against as 1 0 0 0 1 0 0 3 2 3 0, right? And we would represent H as different vector, right? So we can take the whole row and then use it as representation of the word. Okay, so with this, we now have context, right? The context that we are talking about here is the context in terms of the appearance of the word in the document. Okay, so this is one thing that can be done. We can also do the contextual things like this as well, having the word across word and then count the number of times it happens. So in this type of representation, it would encode not just the value itself, but also the frequencies that word appears into the code. One thing you can notice here is that, well, against, how do you get this number out? So if you got a document and that document contains the word against with against, then count 1. If it contains against with h, then count 2, and then you kind of count them together on the occurrence of this word crossword. Okay? So what we have would be the representation that have the value highest at the diagonal. That's for sure, right? Because it has to appear together with its own somehow. Right? You kind of use the word twice and then it appear together. And some word might not be related to another, like this agent and edges. Right? But there are problems here, which you can see that edge and edges, well, they have different representations, but they actually reflect to similar meaning. Now, this is a problem, right? So word cross with word, it's not the combination between word and word, it's not the solution. So there must be something else. You can also represent the word with the context, just like the word in document. Words and discourse represent the word as the appearance in different discourse, different contexts, like whether it appear in the question, statement, or different contexts. This is used in the switchboard corpus, which is the telephone call. Okay. Or you can use the scaling way that instead of counting 1 here, you can count whether the word appears together in terms of the window. If one word like change is close, if this is like a flat window, if one word is close to another, then you can call that can and change appear together. If person and change occur in the window of 3 like this, then you can count it as 1 in the preceding methods. Or you can have a little bit of tuning that you have the scaling value. So instead of counting as 1, you can count it based on the distance from the center. So the further from the center, the smaller the weight would become. Okay? In this way, the scoring function would take into account of the how close of that word to the contextual word underrepresented. And then what was next? It would be the summation of all the weight together, just like the previous slides here. So for these, what you will have would be the representation of the word, that each word can be represented by, instead of a one-hot vector, now you can represent it in this way. So let's look at this one. This one is interesting. Right, you can see that actually has this appearance in this discourse, and it also occur in here anyway. So and if you look at these two words, you can see that they are quite close to one another. High value, low value, and for definitely and exactly as well, that they are quite close to one another in terms of the discourse. Right. So with this, you can compare whether which word is close to which one. Now you have a better representation now, because if you think about using one-hot encoding, well, one-hot encoding doesn't tell anything, right? It just say that this word happened. It doesn't say that this word is close to which, right? So there is a better way here, right? By just not using deep learning at all, right? By just counting the number of appearance, and then you get the code book, the different code book out. This will lead to the next topic of the learning representation later on. And then once you got that vector, you can compare the similarity using something like Euclidean distance or cosine distance if you want to know whether they are just going to the same direction or not. Right. So that's the way that you can do. Okay. Another way to represent the word is to perform reweighting. Okay, what is reweighting? Okay, reweighting is a method that you can use the occurrence of the word to amplify the importance of the word. Like instead of using just frequency of occurrence, we can revise it a bit, right? Recalculate it a bit so that it has the meaning encoding with it. And this is for another class, for the text analytic class. Just a thing that is relevant to what we are going to see next, so that's why it's here. So it means that for each word, instead of encoding it with just this is the approach for the back of word, that the document contains these words, and then for each word, instead of just counting the number of times it happens in that document, you change it into values. What value that would be acceptable? The value like the TF, IDF, the term frequency and document frequency. The value like the probability. I just sum them and then see how many times that it happens. Okay, so these are the reweighting approach. But you can see that all of these approach require certain bias that the investigator, the modeler, has to improvise, has to think of a way that will be the best representation for that types of model, or that type of data model to be used with the technique later on. Okay. So the problem is in terms of bias. Human has bias, and things that are created by humans also have bias. WordNet has bias because it has only a certain corpus that it would cover. Thai text segmentation has bias because it was trained based on a certain data set that is used to train. It would not perform well if you use it on another corpus. It contains certain bias there. Okay. So now representation also contains bias, right? Whether you use TF, IDF, whether you use the other types of representation, that would have to be compatible with the model that you use. All right. Now, if we think about deep learning, what we have learned so far in the deep learning, like this is like lecture 10 already, right? What you can see that the approach in deep learning differ from the approach in other fields in machine learning, in the sense that deep learning try to learn the representations, right? It doesn't impose that data should be represented this way to work best, but instead the model has to learn those representations from the data. What would be the best representation that allow the differentiation between the class? That's one thing. Or in the sense of what we have used in image processing, right? What would be the best feature to detect in order to perform image classification? So you and also even in feed-forward network, right? It has to extract the combination of features that need to be combined before using in classification. So in deep learning technique, the core idea is to learning representation and learning the task. Okay. Now, if we look at the method that used with RNN last time, you can see that what we did there was not to encode it into the something, not letting the model learn the representation, but we kind of impose that the representation will be the one hot encoding, and then you just have to remember the sequence of 100, which make, well, the model can accommodate that, but think about it. Because of that, the sequential model has to learn representation, which is not their job, right? Their job is to learn the state change, like in the sentence, in the state speech, in the text, there are certain state change. You need to learn those, but instead you need to also dedicate resource to learn representation. So that's not good, right? That's why when working with text analytics, when working with nowadays a lot of work in deep learning, it is a good idea to have an encoded representation that it can learn to be the best feature out, just like in convolutional neural net, that it can learn the best feature maps. In neural net, in the recurrent neural network here as well, you can have the model learn the representation of word, and that would fit the data better. We are talking about a word vector. Word vectors are dense vectors. What does that mean? It means that for each word, it would contain just a vector, just like this. one vector, right? This represents certain word. Okay, this vector will have the dimension that is a lot less than the total dimension of the data. Okay, so the technique here is quite similar to SVD, singular value decomposition, principal component analysis, that it tries to reduce the data to the lower dimension. But instead of having using the matrix decomposition to reduce the data, having like deterministic approach like that, in neural net you can have the model learn the best representation that can be used to classify, used to work with the data itself. So what does it mean? It means that what we want is to have this matrix. And this matrix, if you combine with, this matrix is a lookup table. What does it mean by that? It means that suppose that you have this one hot vector, then it will look up just one row out. So this means that you can have this representing every word in your corpus to be used. And you can compare them as well, compare them one by one, and then you can create such a thing like this graph that could tell us that, okay, tiger, gorilla, they are, and lion, they are close to one another, which are different from hamster and rabbit, for example. Okay, the technique that encode the one hot encoding vector, encode the sequence of words into a vector sequence here, is proposed by Mikolov in 2013. This is a framework for learning the word vector. Okay, we would look at the mathematical detail of this one later on. Okay, the idea is to have when you have a large text corpus like Wikipedia, and you have a fixed vocabulary which you know, the idea is to learn the contextual vector. So you need to the algorithm need to go through every position in the text, and it would have the center word C and the context word O, just like what I showed you earlier. Right, it has the center word and the context word. So this would, for Mikolov approach, this would be the center word, and the rest would be the context word, right, in the blue here. Okay, and then use similarity vector for C and O to calculate the probability of O given C and the others as well, and then adjust those word vector to maximize the probability. Well, let it sink in a bit. What does it mean? It means that the model need to learn, need to keep adjusting the word vector. It need to learn the word vector that would maximize the probability. What is the probability here? The probability between the center word and the context word, right? The context word O. Right? How can we do this? Right? There are two approaches basically to be able to do this. The first one is called the Sibo, and the second one is the Skipgram. And the one that I use is to use it's more like the Skipgram here. So what is Sibo? Right? Sibo is to take input and then learn the projection and produce output here. So the input will have you have like the contextual word as input, and this contextual word should predict the output, which is the center word. While in the Skipgram, like you use just one word and then try to predict the contextual word. Okay, well, this might look a little bit complicated, but you get it when you see the actual way to do this. So for example, in the Skipgram, instead of implementing a network like this, you can say that, okay, if the words is in the same context, then it means that suppose WT and WT minus 1, these are in the same context. It means that if you use them and then compare to one another, it should have high value. Right? If it's out context, then it should have low value, for example. Right? We'll look at the architecture later on, how to build this word vector out. Okay, so in this type of model, we have an input vector. Input vector need to pass through the embedding layer. Right? This embedding layer will be the representation here of the word, and then finally it will be used in the calculation or the output layers. Okay, now how do we learn the embedding layer? Okay, we will look at the architecture, this one, but let's first define what are the context words. Well, when we have the word at the center here, change, it's at the center here, center T, and if we say that we have the window size of 2, it means that the contextual word would be 4 of these, right? It would be person, can, the, and course, right? These 4 words will be in the same context as change. For the, these will be these 4, okay. And the rest here in white, these are the word out of context. So for each word, if we use the window 4, for each word we will have 4 combination of the center word and the context word, right? That means number of contextual pair will be quite large, depends on the number of word in your document, right? So how would we learn then? How would we learn what should be represented here? Okay, the architecture of the to learn the word vector can be done by this. So the input word here, for input that are in the same context, right? We will pull the representation out of the embedding layers. Okay, so each one would have its representation, and then the word would be dot. They would be dotted. Once they were dotted, you get certain score. If they are similar, the dot product should produce high value. If they are not similar, the dot product should produce low value. Okay, so then you can pass this through the softmax to sigmoid function, and then if the value of the sigmoid function is 1, then it means that you got the contextual pair. If it's 0, then it means that you got the uncontextual pair, right? The out of context pair. Okay, and then let the model learn like this, right? So it's like learning to do regression instead of learning to do classification, the binary classification. But instead of performing binary classification per se, what you are doing here is to performing pulling the data from the embedding and then adjust the weight in the embedding, and then do that iteratively. So in terms of the mathematical formulation, for word to vec, for each position T, it will predict the contextual words within the window of size M. So that means we have J between minus M and T from 1 to T, and then you to get the loss function, you multiply the probability together. You get this probability likelihood function. Sorry. And then for this, we can get the loss function by minus log, and then you get the loss function J theta, and this is the minus log of this. You get log of P. And so the problem would be to minimize this objective function, which is this would be the minimize the matching, right? The matching between the matching between the value. So what does that mean? Means that suppose that the probability is less than 1, a lot less than 1, then log value would be negative. Log of negative encountering positive negative would get positive value. That's why you got loss in that sense. Okay, right? So how do we calculate this conditional probability? We use the two-word vector, and then if they are in the context, then you should have high value. Okay, and so that means the objective function would be to maximize the probability from this. We get this from because the center word and context word are O and C, so that it means that this should kind of maximize this dot product. This is a dot product between the U and V, those that are in the same context. So if they are close to one another, you will see that exponential here would be high value, and the same here, so that you get the value about 1. If not, they are out of the context, then it will be 0. Okay, so that is what it's supposed to be. So the idea is to use optimization in order to trying to optimize this J theta. Okay, and this is the result of the softmax. Now you can see that there's a problem here. In machine learning, usually you need both positive and negative samples. Now we have those words that are in the context, but we still lack of the words that are out of the context, and we know that there are a bunch of them. Okay, we know that words that are in context will be in the windows, but those that are out of the context are those that are out of the windows. And because without those, the model would just learn only the contextual one. So instead of that, we can plug into the model as well another criteria. This is called negative sampling. Okay, a negative sampling is, if you look at this, just think about this as pulling the value that are out of the context and then add it to the loss function. So if this value need to be low, right? That's why there's a minus sign here. The value need to be in the opposite direction of the earlier. Okay, so this would balance the two. It's called negative sampling. The result of learning produce word pairs that are close to one another in terms of the meaning, in terms of the context. It produced the word representations that can be compared to one another. How can we do that? Like you can compare, you can represent it. This is the two PCA projection of the embedding, to project it into 2 dimensions. And if you look at this, you can see that, for example, the left hand side here are all countries and the right hand side are all cities. How would the algorithm know? It knows because of the location, because of the context, and it has often been used in such a way that it kind of group them together in this form. Okay, so what it means that by using embedding, right, the algorithm can learn the representation by adjusting the codebook, adjusting the embedding matrix in such a way that the words that are in the context would have value of 1, high value, and words that are out of the context can have value 0. You can experiment it by creating deep learning model that looks like this, right? and then performing like performing the dot product like this would trying to it would learn the weight this way. We will look at this type of architecture again in, I think, in the next lecture, I guess, when we look at the Siamese architecture. A Siamese architecture is an architecture that has often been used nowadays with deep learning because it requires, or is called the zero-shot learning, or one-shot learning. The one-shot learning is like you just train it once and then it can work without training in multiple times. This is similar to that because it's used something like the same learning parameters, the embedding. And these and then words are pulled from the embedding to compare with one another. So you have something like a twin and compare with another, and then if they are the same, you get high value. If not, you get low values. And it allows you to build the representation this way. And this embedding matrix can be transferred. It can be used by the authors. So if you search to find the representation, you can find that there are a number of versions of embedding vector of the pre-trained model that you can use, which means that if you were to use a word that is already trained, you can pull that from the existing dataset, the existing model, because it would have the representation that is trained based on a large dataset. Okay. So uh, so this is the first part about the embedding. Let's take a look at what I prepare, and you can see how that works in the code. Okay. All right. All right. Let me open it. Okay. Document Python deep learning. So it's lecture 11. I forgot to change the name, and should be the word representation. Right, it's embedding representation. So these are the codes that are in that are also in the lecture, right? So you get the WordNet part here, which download the WordNet, and LTK. If you are not installed this, it's fine. Right? We will not use it anyway. Right? And you can use it to retrieve like WordNet and then infer the meaning from that. Right, and this is the code to train the Skipgram model. Okay, let's look at the dataset first. Oh, no data. There should be. Let me look at the data first. Okay, no data. Let me put it into the group for this data set. Right, this one. All right, I just uploaded the data to the group. And let me copy it to that location as well. All right. Okay. Right. So this is the data that I've used is the data set about car, the model of the car, and the explanation in text and in category in some types of sequence of text here. So instead of interpreting this as what I would demonstrate here is the ability to learn the context for embedding vector. So what I would do is to combine the make and the model together so that I will get the make model here. make model. And then what I'll do is to just extract the categorical category and then combine them into just one vector. So this would be like a sequence of description. And then clean it a bit so that we get the column clean here. And split it into a sequence of vector. Okay. Now, once you got a sequence of vector like this, you can train the Skipgram model. You can train the word2vec to get a vector. Here I use a vector of size 300 and then train 100 iterations. The size here refers to the number of dimension that is allowed. Default is 100. Window is the distance, like what I said. When you do the Skipgram or when you use algorithm to scan for the context words, you need to have like the center word and the contextual words, right? The window here would be the size of the window that it counts as contextual, right? So default is 5. Mean count, this is number of time that a word occurred. If it's less than that, it will be excluded. So it's 5. Worker is number of worker. SG is the algorithm. 0 for Sibo and 1 for Skipgram. Default Sibo. So I'll use Skipgram. This one is set to 100. And run. Word2vec not defined. Yeah, forgot it again. I need to import from gensim import word2vec. Actually, don't remember. Gensim and the package word2vec. Import gensim model, sorry. Yes. No size. Well, it's kind of, it's probably changed. Yeah, it's probably changed this. Now it become vector size. No iteration. Actually, you can just remove it. Probably change to author names, which I need to look at that later on. Never mind. Let's remove this. And how about SG? Still there? Yes. So with this, now we have the word vector for different words that are there in this sequence of in this vector of tokens. Like we can take a look at Toyota Camry, and then we have the representation of Toyota Camry, and the size of 100. And then we can use this to compare the similarity here. I compare Nissan Van and Porsche and Porsche Cayman, and this is a similarity vector 0.74, and with the Benz this is 0.96. Right, the explanation are similar comparing to the others, right? And find the most similar to Mercedes, you get this Maserati and the others here, sport cars. Okay, when we compare the similarity, what we are doing is compute the cosine similarity between vectors. Like you can compare whether the vectors are similar to one another or not. Okay, for the cosine similarity can be done manually. This is how to do it. To illustrate this, you can just compute the dot product and then normalize by the size of the vector. Then you get the value out. So this would be the function that take in the word vector model and give in a word and work in the target list. And this would be like the the column that you want, and then you get the number. Yeah, you get the number of item out that are the most similar to the target word that we put here. The codes are to just compare one by one by each. So specify the word, right? You retrieve the vector of it out and compare to another. You get you kind of get the entire list of words that are there, and then you want the results to be extracted from the column in the target list. In this, the maker model. Maker model is this column maker model. Okay, and that's the results here that is extracted. Okay, so this is to extract the column maker models, and then put this vector into this one so that it can compare this word to the maker model and find the most similar one, 5 most similar one. And oh, sorry, wrong here. It's not subscribable. Should be WV here, right? And then it can extract the list out. So this is the implementation of the similarity above, like this one. Right? So what it does is to compare the target word with the remaining, and then determine which one is closest to what you are looking for, and report it, sort them out here. Okay. And this is a function to plot the T, S, and E, and you can plot. Oops. Word to vec has no attribute similar by word. I forgot again. I need to use WV here. Down here again. Model test and 12. The dimension is 100, not 300. Okay, yeah. Sorry, there's yeah, for the model, in order to retrieve the word vector, you need to use the WV interface to retrieve word vector, similar to find similar word. And I changed the size of vector to 100, so need to change it here as well. Right, and here you will display the car model here that are close to have the explanation close to what we put in there, which is Porsche 718. Porsche Cayman. How about Yaris? Here for Yaris, we got CRC, Yaris itself, and Matrix, not in Thailand, Renault, Mazda 2. These are the cars close to this one. And you can see that by comparing the word similarity, it can retrieve the one that is close to another in terms of the context, without even specifying that they are closer to one another. Okay, and this is for Camry. And then we can perform something like this one, that we can use the word vector X as Yaris and Y as hatchback, because Yaris is hatchback. You can subtract hatchback from Yaris, and then add the regular cab pickup into that, and then define the results. And it's five results that should be Chevrolet, Silverado. Let's pick one out. It will be something like Yaris, but not really Yaris. So we will open cab pickup. That's like Yaris. Don't know if it looks like Yaris though. Yeah, something like this, right? Maybe low cost, probably. Right. So what you have seen here are the representation. Right? You can use the word vector to represent the text instead of using one-hot encoding. After the break, we will look at a way that you can use this type of representation in the actual task, in the text classification task. That is, instead of representing the text as one-hot encoding, you can represent the text as embedding vector, and then use the recurrent neural network, the LSTM that we learned last time, to perform text classification. Right? We'll take a break first, and then come back to look at the application again. Right? Let's take 15 minutes break, and let's start on 7:10. Okay. If you have questions about embedding, put it into the chat, and I will come back to answer later on. Sorry. Cut. Yeah. Yeah, it's like, yeah, sometimes we did that as well, yeah, for the Thai class, speak English with them. We're confused. Okay, so what I'm showing you here is also another, I forgot to load this dataset for you again. Let me maybe do that. Did I? Oh, it already has this dataset. That's fine. Okay. What I'm going to show you here is how you can use embedding together with text classification and performing that in Keras. Okay. So first, let's read the data in and take a look. This data, the consumer compliant dataset, has this format. So it has a topic, debt collection, debt reporting, credit reporting, and authors. You can check the shape. This is the shape of this dataset, and you can count the number of times that it happens for each one. And what you can see here is that some of the labels occur, like virtual currency here, also happens in the same categories as the virtual currency here: money transfer, virtual currency, money service, right? And the payday loan, title loan, personal loan also has its own category. So what I'm going to do here is to merge the smaller category together with the larger category, so that we have like a larger set that can be used for classification. Right. So what I'm going to do is just to create a mapping here. This is example of the consumer loan. Get the value out, and then what we get is like this: financial phishing, right? I was getting exact hands-up call day from exam. These are the complaints, the consumer complaints. So we are mapping here credit reporting to be the credit reporting, credit repair, service, and authors, like mapping the larger category in it, so that when we explore again, we get only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 categories, right? And we use these 11 categories for the purpose of classification. And then, as you can see in the above, the text need to be cleaned. So this is the text cleaning, right? To clean the text down here, this is just to print that here is the text and the category. Okay. Then in text cleaning, what we are going to do is to convert the text into lowercase. That's the first step. The second step is to replace the symbol. Okay, remove the symbol, remove X in the text, and remove the stop words, which are the words often occur in English and doesn't carry much of the meaning. and remove digit from the text. Okay, so here I just download the stop word, and this is the function to clean the text, which is just to lower case, replace the following symbol with space, replace the bad symbol with nothing, and then replace x with nothing. Right? This might create problems because x might occur in the word like text, and it will be tet instead of text. Never mind, that's just another token for this. Right, so this would apply the clean text function to clean out the text, right, removing unnecessary part so that we got only the necessary part out. Okay, Natavat just said that I need to provide requirement.txt to install lib with specific version. I don't really remember what version this is. That means you probably need to fix the code to make it work. Yeah, I know. I don't know what types. I don't remember the time. Even the first time that I created this, it might be some of them. I kind of modified along the way. Yeah, so it is updated as it is. Okay. So here, that means after cleaning the text, you can see that it contains like a sequence. It becomes like a sequence of keywords rather than the full text like the above here. Okay, it becomes a sequence of keywords, and then we use this sequence of keyword in performing classification in create a model. What we are going to do is to vectorize the consumer complaint text, and then convert it to the embedding layer into embedding vectors. Okay, so what do we need to do? Right, this is to just specify the constant max number of word, max sequence length for each document. It should not exceed 250 character. No, 250 word. This is fixed. This is embedding dimension. So first, the text need to be tokenized since it's already cleaned. It need to be tokenized. Once tokenized, and you would get the sequence of text out. And afterward, what you need to do is to pad the sequence so that they have the similar dimension. Otherwise, when you use it with deep learning, you encounter the problems that the texts are not having equal size. It wouldn't work. Needed to have like the same size. Wait for a moment. Still working on that. So here, to look at this. These are the word index that is used in tokenization. Okay. And then in tokenizer, we use text to sequence, which will convert the text to the sequence and pad it using the pad sequence from Keras. It will pad it to the same size. And we would get this text and the vector, which you can take a look at here to see its composition a bit before we proceed further. Okay, here's transfer system inc trying collect that my own inaccuracy, and you have this padded sequence and the index for the word. Okay, so this is the index for the word, not the one hot encoding. Because rather than using one hot encoding, you can use index and then perform lookup at the embedding table. Okay, and we also need to convert the output to something like this, one hot vector for the output, and separate the data into train and test, and then build a simple Keras model. This Keras model will, the first layer will be the embedding layer, 100 length vector. Okay, so that means this layer will be learned, right? And it will be the size of the length of the column of 100. Number of rows, that depends on the size of vocabulary, which this based on this max number of word here. The max number of word, if I remember correctly, specified above here is 50,000. So it's quite a lot here. So this we first has a sequential interface to this is to load the old one that I already trained. A sequential interface to declare the model. Add embedding layer first with input length of the shape of x, right? The width of x, and also we add the spatial dropout to drop out some location of the in the RNN learning, and the LSTM dropout with recurrent dropout. These are the dropout for the weight, and finally the softmax. Just one layer of LSTM, and lastly specify that the loss function is categorical cross entropy. This is categorical, not binary, and use Adam here and fit the model. And wait for evaluation. I should specify to use CPU. Will take some time. Let me do this. Well, you can see that accuracy improved by iteration in the epoch. However, not really sure if we should wait for the whole thing to finish. Did I have the trained version? No. So I need to save it first. Right, you know the drill here, right? After you train the model will improve in accuracy, and then you can perform evaluation down here. And you can train it with a new component by using the same tokenizer and padding, and then perform prediction, and then you can get that. And you can even train it using bidirectional LSTM, which take more times to train. Well, so that's it for this one, I guess. So this is how you can build the RNN to perform classification by having the dense layer at the end. LSTM here is the part that takes into account of the temporal feature. I can think about it that way. And embedding is to take into account of the word representations, which will be trained accordingly. Okay, now let's switch back to our topics, because and let it run. Right? I don't think let's just stop it. I don't think it will finish in time of the class. There's like 50 iteration now. After it takes like another 4 hours to finish the job. Let's stop it here. All right. Okay. Um, let's look at this. Word embedding is the part of deep learning theory that address the representation of word. You may think that it is just an application of word text analytics, but it's not. Word embedding utilizes the same notion as a broader concept. This broader concept is known as autoencoder. An autoencoder is a network that tries to learn the lower data rate and then trying to predict the same instance out. Doing that, which would mean that the network need to be able to compress the data down to only essential representation to reproduce it back to the same one. Okay. So instead of thinking about embedding as a particular problem that happen in text analytics, we can think of embedding as another version of autoencoder, right? That learn the latent variable. Okay, because embedding would encode the word character categories, whatever that you want to encode, into latent variables. Right? This is similar to when we perform dimensionality reduction in machine learning, that we decompose the metrics of like utility metrics into just using singular value decomposition into the document and topics, or if we were to use embedding layer or doing the PCA, would kind of compress the data down so that you got the lower dimension out of the data. This concept that you are trying to learn representation that has lower order but can be replicated back to higher order is the concept of autoencoder. In the general autoencoder, it is represented as a feed-forward neural net, where it would take input x and get the coded vector and reconstruct input x, right? So it means that it would have two parts. The first part would be the encoder part, second part would be the decoder parts. Right? The idea is to learn the low representation dimension here. So you have something like image x and then encode it to the latent space z, and then you can reproduce it back to the same image again. Okay. What would be the use of autoencoder like this one? So you can, when you look at it, you can see that the concept itself is very similar to embedding that we talked about earlier. In embedding, what we are learning is the representation of the text, right? That should represent the context, right? It should represent the context of the text. Here as well, what we are learning here in the latent space is the encoding of the image, right? Of the image that could be used to reproduce the same image. So what is the use of autoencoder? You can use autoencoder to perform visualization, right? You can reduce the dimension of the data to be at the lower resolution. You can use autoencoder to perform compression, which means that you're trying to find the low dimension representation. Because say if you have the image the size of 512 times 512, and then you want to compress it to just say 128 to 128. That's a lot of compression there, right? So in order to do so, you need to design the network so that here in the middle you have the size of 128 times 128. Okay, so you can use it for compression for sure. You can use it to reduce the noise, because by reproducing the output, it would generate only the essential part, not the noise part, the high frequency part. Okay, so you can use it to denoise the data, and you can use it to learn the abstract features in an unsupervised way. So like learning the centroid of data from the unsupervised data, and then you can apply that to train the model later. Let's take a look at the concept that is close to the autoencoder. PCA. Right. PCA stands for the Principal Component Analysis. This is a technique that decomposes the data into lower dimension, okay, without using neural network. Okay, the data would need to be normalized first, and then we would need to find the covariance between features. Right, find the covariance between features. The covariance is the variation comparing x and the mean and y and the mean, and find that they are covariant together. Once you get this covariance, it means that you get the square matrix. Once you get square matrix, you can use the eigenvalue decomposition to decompose the covariant matrix into eigenvector and eigenvalues. Then you can use this eigenvector to project back to get the lower solution of the data set. Right? This is the concept of principal component analysis. It's often covered in the machine learning course and used there. For PCA has been applied to more than just one dimension as well. It has been applied to like 2 dimension, to like facial data. And then once you decompose the multiple faces into the like eigenfaces, right? These would be the eigenvector of the face, which means that you kind of if we work at Facebook and we got the face data, we can use the face data to learn the general pattern of the face and call them the eigenface. And then for each of us, like for me, my face would can be described as a weighted sum of these faces. Okay, and now you got this weighted sum, you can use this coefficient to perform like face verification, such that without using deep learning at all. Okay, so PCA allows you to do that. Right? It also allows you to represent the data of the digit as well. That you can from multiple variation of the writing, you can decompose them into the vectors. And then once you use this vector to reconstruct data backs, if you use just a few of them, you get like blurry image. If you a lot of them, you get well-defined image like this. Okay, PCA itself, in the mathematical concept, is an autoencoder. Okay, you can see that PCA in the PCA algorithm, we need to calculate the covariance. Right? Covariance would be the variation of one variable comparing to the variation of another variable. Right? Comparing the covariation between the 2 columns. Think about this as, suppose we have a table, and x and y are the data from different columns, and we are calculating the covariance between 2 columns. Right? And finally, we would get the square matrix of the size of variables, the size of the features. Then from that, we can then reduce reduce it by using eigenvector decomposition to reduce it like this one. Right? Reduce is using the SVD to have lower, actually reducing it to something similar to SVD, but using the metric decomposition to be eigenvalue and eigenvector. With eigenvalue and eigenvectors, we would have the representation of the main axis and the secondary axis, like this. So PCA is used to learn the kind of the direction of the data, and then we can use those direction of data to project the point onto those axes. Okay, so the method of PCA itself is autoencoder problems, and that trying to minimize the square loss here between x and x tilde. X tilde is the reproduced one, x is the original one. Okay, and x tilde comes from the multiplication of v with a certain matrix v, x with v and with u. So these are the transformation from x to k unit here and then to d. So in PCA, the idea of PCA is to get the value of k that is lower but still represent the data, right? Lower than D still represent the data. Okay, so if K more than D, it doesn't matter, right? Well, if the unit here is larger than D, then you can just copy the image to the end, and that's it. And not interesting. If K is less than D, then this is interesting because it will become compression, right? This is the dimensional reduction. So we would map X to K, and then to this layer, and you would map this layer, the K dimensional subspace, into the D subspace. Okay. This mapping X multiplied by V can be thought of as a projection of vector. What is the projection of vector? When you have one vector and then you dot product the vector with another one, that's called projection. This projection is the same as the light projection that you shine a light to the tube and then it reflects on the wall. Right? This is the same thing. Right? In mathematics, when you have two vectors and then you dot product between the two vectors, this is the process called projection, because you are trying to compute the element of one vector on that another vector. Right? What will be the impact on that vector? Okay. So if we have this point X in the blue, and then we have this plane, the projection of the plane of the point to the plane would be the multiplication of the point and the unit vector that is perpendicular to the plane. This is calculus back then. Right? In the calculus, when you learn, I think it should be in the calculus 3, that you learn that, okay, when you have line, you have plane, you can have a vector that is perpendicular or orthogonal to the plane, and you call that the unit vector or the normal vector. And those normal vector, if you want to project the point onto the plane, you can compute the dot product of the point with the plane, or with the unit vector of the plane, right? And then it will transform into like the point on the plane. Okay, so that's the idea. So it means that the data point, it need to be this is the projection, right? So what we want to find is to find the line here that should be like the core vector, that should be the plane that represent the variation, and then we can reflect that variation to that plane. Okay, and this plane would have the dimension that is lower than the original point. Okay, that means we have the D unit here, and means suppose that we have like 100 columns here. K can be 10, can be lower than that, and it would reflect the compression between D to D, that you have like the lower resolution in the middle. Okay, that means if you create a bottleneck in the network, right, it doesn't have to be just feed forward. It can be convolutional network as well. If you create a bottleneck in the network, and then let the input take, let the model take the input and produce the same input, right? Use the same input as output. Then you are trying to learn something in between, right? You are trying to learn representation that can encode the whole data set, right? That this representation should represent the core variations of input and the reconstructed image, right? The technique is just like this, that you can plug this data into the feed-forward network and then kind of creating a bottleneck. And then what you get would be the compression of data. So this is the results of doing the autoencoder, right? Linear autoencoder can learn the code, and then once you reconstruct it from the lower resolution, like using only 30 dimension, with the autoencoder you get the data that is closer to the original one, but with CCA, because it doesn't learn directly from the data, your data kind of get blurry. That means there are a lot of details that are lost in the process. Okay. So autoencoding can be created by just like creating a bottleneck, and then you got this latent space representation. I think if you are interested in this type of research, it would be interesting to see the implementation of bottleneck in different types of network, like in RNN, in CNN, right? Because usually an autoencoder is thought of as like part of the feed-forward network, but it can be applied to other as well. And you can see those in the multi-hierarchy, right? Hierarchical constructs. Like if you look at the YOLO, right? The YOLO in object tracking, you can see that if you look at the research paper of YOLO, you see that they utilize some types of multi-hierarchy, that each hierarchy has different resolution, and that means they create a types of lower resolution, lower, to get the latent representation out of the data and then combine them later. You can see in those paper if you choose to work on that topics. All right. This is the topic about autoencoder. Right? The remaining slides are the thing that I have already talked about, the text classification, which actually I should put it before this one, which should be better in terms of the sequence. So it would repeat the same thing that I did, that we look at in the slide. Okay. Nothing else. All right. Okay. So this would be the end of today's lecture. For your assignment of the RNN, I will post the assignment sheet to the group. You will need to create the recurrent neural network to perform text classification or sequence classification without embedding, and then compare the result. I will try to I will test in my computer first. That will be fine that way, because my computer is very slow these days. Yeah, and if it works here, it should work on your end as well. Okay, so this is the end of the recurrent neural network lecture. You can select the topics to do the research study on this recurrent neural network as well. It would be interesting to see that in the research. RNN has been combined with other models, has been used in the sequential data in a lot of models that are related to sequential data, and there are quite a number of modifications further from just the LSTM and the GRU. And if you are interested in the core model, I would encourage you to look at that. Okay. All right. Now it's time for question. Do you have any questions? In the RNN, you can see that if you want to create a classification model, at the end you need to put the softmax here at the end, right? And then let it work at the end frame to perform classification like that. Okay. Any question you like to ask? It turns out that the university does not allow us to have the exam at on-site yet. So for the final, I think we should do the take-home. That would be better, right? Instead of having the to like using the online platform. That's for the graduate level. I expect you to write a lot, design architecture and solve the problems. So let's do the take-home exam at the end of the semester. Okay. Next time we are going to look at what topic? Next time will be about Siamese neural net. All right. Okay. So the next time we will look at why do we need to create the embedding model that way, and we also look at the Siamese neural net in the face verification applications, and that will be fun. Right, and then also the theoretical underlying of the Siamese neural network model. Okay, so then let's end it tonight. See you again next time. You got 2 weeks left, and then it will be your turn to do research presentation. I will. Have I posted the link to the group yet? I don't remember. Can you tell me? Teach too many classes this semester. Did I put the link about the paper onto the group yet? No, I don't think so. Okay. All right. So I'm going to put in the link and the reservation slot for you to reserve your slot in your research discussion, right? So the research paper that you pick and present to the class, the thing that I want you to present is the deep learning technique in those paper. You can pick the application paper and then discuss about the approach in the application paper. That's fine. Paper related to the application, like the use of deep learning in GPS in map, for example. Or you can pick the papers about the core architecture and discuss about the core. That would be interesting. Or the technique that I have not covered in the class, like where we look at RNN, we look at our LSTM, we look at CNN, but we may have not looked at the technique like YOLO or mass RCNN or the application of attention, which we will talk about it next time, actually, the time after the next time, actually, or the multi-hierarchy model. Right? If you are interested in those, you can pick those and then discuss in the class. Each of you would have about half an hour for presentation. Actually, there's not much of the strict rule on the timing, but approximately half an hour to present the topics that you choose, the paper that you choose. So that should be about it. So the criteria is that you should be able to articulate the concepts in that paper, the deep learning concept in that paper, and then how it works and why it works. Okay. I will post the link on about the slot of the presentation to the groups. You can register yourself into the slot that you like. We have like 2 days for that. Choose one and choose the time slot that you like, and that should be about it. Okay. All right. So then see you next time. We'll look at the Siamese neural net next time. Okay. For today, have a good night. Another thing, yeah, I will post beside the link to register, I will post the assignment. You got 2 weeks to do that.